Swayam Prabha, free DTH channel for education.
Hello everyone. In this recorded video lecture, we'll continue our discussion of histogram based image enhancements that we were doing in our previous video lectures. In particular, in the last recorded video lecture, we posed a couple of questions. So we'll start with a brief discussion of them, followed by few other histogram based equalization methods. By the way, the answers to this couple of questions would be very brief in this recorded video lecture. We had a detailed discussion about them in the Zoom session that also which I uploaded into the YouTube channel. So please go through that for a more detailed discussion. In that Zoom session, I have taken up one analytical problem related to histogram equalization. So please go through that as well for more clarity about histogram equalization. Now let's start with the questions that we posed in the last video lecture. The first one being, when you are applying histogram equalization, essentially you are making use of the cumulative distribution function and moving from your parameter R, you are mapping that to a new parameter S. So what would be the nature of this transformed variable S? As we discussed in that Zoom session, this variable would be a monotonically increasing function, which means we know for sure for each R a unique mapping or transformation to S. But in case if you want to find out a inverse transform for this, that will not be unique. In that Zoom session, we also discussed that although there is no ideal solution for it, some strategies that are commonly followed in order to deal with this non-unique inverse transform. The second question that has been posed is, let's say instead of a equalized histogram, our objective is to map the histogram of the current image to a reference histogram that we know because of our prior knowledge about that particular image. How we can achieve that is find out histogram equalization for this given image. You get one transformation here. For the target histogram also apply histogram equalization. With the transformation you get another histogram here. Now for each value here you find out the corresponding mapping here in this histogram. You take the same value here and from now you compute the inverse transformation here, and from that you will know where this would map to, and that is what the intensity with which you replace the intensity with which you started in the given image. So again, this non-uniqueness of finding out inverse, we discussed it in some more detail in the Zoom session, so I leave that part at that point, so you may go through it for more details. I just want to show you few examples again taken from Digital Image Process book from Gonzalez and Woods. This is for example the image of one of the moons of the Mars captured by NASA, and now if you apply a simple histogram equalization, this is what the histogram will get transformed to, and this would be the resulting image. On the contrary, as many images at different time instances of the same moon would be captured by the satellite or whatever, so from that, under a good lighting conditions, you might be having already a good knowledge about how the histogram should look like. So this is for example how the histogram should look like. Now you use this as the histogram specified and apply this histogram specification, and then you would end up with this image. As you could see, the contrast or the quality of image is much better now. Let's now discuss two more methods one being local histogram equalization. In practice, there could be many instances where you would like to apply this histogram equalization over a given region rather than the entire image, because that will not be capturing the characteristics of that particular region, or in some other instances the shading or illumination could be varying over the entire image at different parts of that image. So if you are using just a single histogram for the entire image, that might not give you the best results. So this is exactly what the objective of local histogram equalization. There are different ways this local histogram equalization is implemented. One way that you will be going to implement in your assignment is that for each pixel you take, for example, a window of size w1 by w2, or assume that you are taking a square window, so you take a window of w by w size, and for that neighborhood you find out a histogram, and for that histogram you do histogram equalization, and then you look at the intensity of that particular pixel here and see where it is getting mapped to, and now you assign that particular intensity to the pixel which is at the center of your window. Now you slide your window and you repeat the whole process and find out for the pixel, for the center pixel of that moved window or slided window, now what is the corresponding mapping intensity, and you replace it with that intensity. By the way, local histogram equalization is also commonly referred to as adaptive histogram equalization, and because it is adapting based on where that particular pixel is and what are the intensities of the pixels surrounding that pixel, right? So this is also referred to as adaptive histogram equalization. The way of implementation that I just mentioned, where you would be moving your window throughout your image, and while you every time you move it, for the pixel which is at the center of your window, you compute the new transformation by taking the histogram over your window. Now you would be replacing the intensity of the pixel which is at the center with the new mapped intensity that you have computed from your histogram equalization. So this is referred to as adaptive histogram equalizations. In fact, there are many other ways of implementing as well. Like for example, this is one way that people typically implement for computational efficiency, is that let's say you in this example you have divided your image into 1 2 3 4 5, I guess, right? 5 by 5 windows. These are typically referred to as tiles. Okay, they look like tiles. So now for each of this tile you compute histogram, and you compute then histogram equalization, the histogram as a result of applying histogram equalization, and then again you would be classifying the resulting pixels, the pixels that are there in the entire image, into three types: those which are at the corners, those which are at the edges, and those which are at the centers. You deal with them in a slightly different way. For simplicity, just let us take a look at those which are there in the center. Okay, for example, this is a zoomed version of this block. Here you would see now this tile which is in black, assume that this is your center pixel for which you have histogram equalization. Similarly, for every pixel you will take 2, and on top you will take 2. Okay, bottom you will take 2, on both left, right, top, bottom, and you do an interpolation now between these histograms that you have obtained here based on that, and then you figure out this. Anyway, this is one of the many possible implementations for computing the local histogram equalization. But anyway, for your implementation, whatever I mentioned, which is usually referred to as sliding window adaptive histogram equalization, is good enough. Hope it is clear. Now you could notice that when we are using a local histogram equalization, there could be regions which are more or less uniform with slight variations in intensities. Then what would happen? That slight variations here and there are some due to noise. There could be few points, okay, which have high intensity, but you could clearly notice that in such near contrast region or a uniform region, when you apply a histogram equalization, that would amplify the noise a lot, because everywhere you are trying to spread it, all the intensities that are there from 0 to the maximum intensity level, and then you are trying to achieve an equalization there. So in practice, in addition to adaptive histogram equalization, it is quite common that you would do one more modification here, that's referred to contrast limited adaptive histogram equalization. Let us see what it means. Although we are drawing here continuous, you could think of them as discrete version of PDF as well for histogram. So you would take a upper cap on what could be the maximum value in your PDF. So you, for example, you clip it here. Okay, so then this would be whichever is there, this is clipped here, so all this would have this value now. So if it is greater, you just keep it to this value. Okay, this value also you keep it here, and then to again convert it back into a PDF, you would be uniformly distributing these values to all the values of intensities. So this could, then what would happen again, you are raising the base for the entire histogram uniformly. So because of that, again what could happen, the pixels particularly here, they again would cross the upper value for this PDF that you have decided. So then what you do, again you take this values and uniformly distribute across all. So this you would be doing iteratively until there is no value of intensity or for which the PDF is greater than this predetermined maximum value. And then on this one you would be doing histogram equalization. Again, this you could do locally, so that is when you refer to it as contrast limited adaptive histogram equalization. Here is an example for the same image where you are doing a clipping, then you are redistributing it uniformly across all. That would again bring it back for some intensities above the upper limit, that again you clip it and redistribute it. So again here you have different parameters to choose. For example, what should be the maximum value, that's one thing. That is as far as the contrast limited part of your method is concerned. And the second constraint could come from what should be the size of your neighborhood. Let's say I think they have taken here a size of 25 by 25 and a clip limit of 0.05, that was giving them the best result here. Okay, just wanted to show you another instance. This is not a contrast limited adaptive histogram, a simple adaptive histogram. This is your input image. On top of it, if you are applying a histogram equalization, this is what would happen for you. Because this is on the dark region, in a histogram equalization, the pixels which are dark would become much darker and which are light would become much lighter. So this is what you would end up while you are applying it. On the contrary, if you are considering a window over each pixel, and if you are computing this histogram over the window centered at that particular pixel and then doing the transformation, this is what you would end up with. So you could clearly see the advantages of adaptive histogram equalization. That's all for image enhancements using intensity transformations. These are all point transformations also referred to. From the next video lecture onwards, we will go to neighborhood based image transforms, so where you would be using the kernels, or you could also call it as convolution or correlation based image transforms, where you would not only look at the intensity of that particular pixel, but you would take a call on to which intensity it should get transformed to based on its neighborhood pixels. By the end of this week, mostly the first programming assignment for you will be uploaded into the Moodle page. I just wanted to give you some idea about what this assignment is about. So you will be given the chest X-ray images for I guess 4 subjects, and you need to apply different transforms that would give you better enhanced images. Say for example, in one part of that assignment you need to figure out by visually looking at the results which gamma correction would give you the better results. So that's one part of it, and then you need to apply on them a histogram equalization to get a better contrast. That's part 2 of your assignment. And then another part is you have to do adaptive histogram equalization, and these three you have to implement your own codes for doing this. And for local histogram equalization, your code should be in such a way that it is at least optimum in some sense. That what exactly I would discuss with you in the Zoom lecture. That's what the third part of your assignment. And for all these three you have to write your own codes. You should not be using the built-in functions for doing those enhancements. And then the final part is where you could use the clipped adaptive histogram equalization built-in function in MATLAB. Similarly, in OpenCV in Python there is also another function for doing that. You could use this existing built-in function but then experiment with various parameters that are there for this algorithm. Okay, so that's all for now. See you in the next video lecture. Take care. Bye.